All right, so 13.6, we talked on Friday talking about this conditional probability, okay? Conditional probability being that if we're interested in the probability that an event occurs given that or provided another event has already occurred, okay? And we worked through and we found that that was equal to the probability of A and B divided by probability of A, okay? Now, we also taught, we drew the comparison and maybe understand where that came from by looking at this. We knew that if, I think what we talked about was, like if we have, let's say 3 red marbles and let's say 7 blue marbles, okay? And I take, and I want to know what is the probability of getting red and blue, okay, red and blue, when we pick 2 marbles and keep the first one out, okay? So that would be the probability of red times the probability of blue. Does that make sense? Okay. So if I take, and I'm going to rewrite this a little bit different because right now we're saying we're going to keep. So this is without replacement. So if I were to do this, the probability of red would be what, 3 out of 10? Does that make sense? But now the probability of blue would be 7 out of how many? Because I kept the red one out. 7 out of 9 now are blue, right? Okay. So this one, this probability changed because that one already happened. Does that make sense? So the probability of red and blue was equal to the probability of red times the probability of blue that the red one had already been chosen. Does that make sense? That's why I write it that way. Probability of blue given the red one was already chosen. Now, if I want to reorganize this, okay, to solve for probability of B given R, then it is the probability of R and B then divided by the probability of R. Does that make sense? Okay. So if I want to know what is this probability, and think about this, if I want to know that, so that number is 7/9, right? We already know 7/9. Let's say the 7/9 equal the probability of red and blue. So red and blue would have been this, 3/10 times 7/9 divided by probability of red, which was 3/10. Those 3/10 cancel out? It leaves me a true statement, right? Okay, so we know this is true. Okay, that's our given that, or what we call our conditional probability model. Okay, and with conditional probability, I mean they're dependent events. Okay, if they were independent events, then this given that stuff would not matter. Because think about this. Okay, if there, what's a scenario? You guys remember any situations that were independent events? Okay, so a spinner and a coin toss. So let's say that we have a spinner and it lands on yellow, and we, given that we've already flipped a coin that was heads. Okay, so I want to know what is the probability that I get a yellow on the spinner given that a heads has already shown up. Well, because those are independent events, one does not impact the other, right? So doesn't it make sense that this would just be the probability of yellow? Think about this. If I have a spinner Well, let's do this because I don't have spinners, but I have dice. Let's say that let's say we get a 6, given that I don't know if I've got any coins either. I don't. I'm poor. I got a bag of popcorn though, so that's going to be our coin. Man. All right, so popcorn's got Orville Redenbacher on it, so that's our head. That's his face, and that's how we tell. So I'm gonna ask, what is the probability that I get a 6, knowing that heads has already shown up? I already know heads has shown up. Does that have any bearing on the fact that I'm going to be able to roll a 6? No. Okay? So when my events are independent, okay, that should be true right there, which generically says the probability of B, given that A has already occurred, if that is simply just the probability of B, then what that meant was that A had no bearing on B. A and B were completely separate events. They do not rely on one another. Okay? Does that make sense? And I can also flip it and say the probability that we get ahead, given that a 6 was already rolled, that would still be just the probability that I get ahead, because the 6, the dice, has no bearing on the coin, or in this case, the bag of popcorn. Does that make sense? So that generically would say the probability of A given B is just the probability of A. That and that are tools that allow us to determine if two events are independent. And the third rule is that the probability of A and B is simply probability A times the probability B, if that can be shown. And that's what we talked about with independent events to be true as well, is that when we're looking for both of them to occur, then that probability is the product of their individual probabilities. If we can show one of those three things, then we can show that the events are independent. If you cannot show one of those three things, then your events are going to be dependent. Does that make sense? Okay. But all of that ties back into our conditional probability. When we talk about conditional probability right here, these events are going to be dependent. Okay. Is it okay with everybody? All right. So we can use the conditional rule to help us see and understand maybe complex events, maybe see and understand complex sample spaces. You can see here it says you can use this formula of the conditional rule when you know the conditional probability. You can also combine conditional probabilities to find the probability of an event that can happen in more than one way. What I'm arguing here is that if you know this, if you know the probability of an event occurring, knowing something else has already occurred, you can use that, and one of these will be unknown, and maybe you can find then the probability of event A all by itself, or maybe you can find the probability of two events happening simultaneously. Okay, so this is a formula, right? And these are three unknowns. If you know two of those, you can find the third unknown, and that's basically what this problem is going to kind of target. All right, so I got a question. I think this helps us with seeing a sample space here. If we draw what we call a tree diagram here, tree diagrams always emanate from a singular point, and then they go down to our certain events. All right, so this is gonna be our sets of events. Okay, so 70% of freshmen had attended public schools. 60% of freshmen who attended public schools graduated. 80% of other freshmen graduate within 5 years. So we've got basically two events. Did you attend a particular type of school, and then did you graduate within 5 years? Does that make sense? Okay. So this school here, I'm going to list it as being private. Oh, sorry, public. Okay. So if it's public, then usually the other type is private, but it could be like a Montessori school or a charter school or something like that. So they call it other. Okay. So we got public and other. Now, if you guys remember doing that, I mean, there's one on the board right now, flipping coins, right? On that whiteboard of different. That's a sample space tree on the left up there on the board as well, with 3 situations, 3 events. But those are our options for school. If I go to a public school, could I have graduated within 5 years or not graduated, right? So here we graduate, not graduate. If I go to other type of school, could I have graduated in 5 years or not graduated, right? So constructing that tree diagram hopefully is not outside of our capabilities. Now the question is, how many freshmen graduated in 5 years? Well, some of those freshmen came from the public schools, some of them came from other schools, right? So we need to be able, we can't from the 70, the 80, and the 60 that they give us in the problem, we can't just add some of those numbers up, because any 2 of those numbers that we add up are going to exceed 100%, right? So what we do is we look at this, okay, 70% of freshmen attended public school. So what I'm going to do along this branch of the tree diagram is I'm going to put 70% right there. Okay? Now, 70% went to public. You automatically then know how many went to the other. How many went other? 30. Okay? That's called a complement. Those 2 things add up to 1, right? Okay? Now it says 60% of freshmen who attended public schools. So you know that we've gone along this branch and we're right here. 60% of freshmen who attended public schools graduated. So along this branch, so you've gone public and then now they graduate. They said 60% graduated. So that'd be 0.6 right there. Does that make sense? So how much would this be? That 0.4 would be not graduate. Okay? So it's 80% of other freshmen graduated. So that should be 0.8 there. So what would this other, that not graduated be? 0.2. Okay? Now remember what the question was. It was the number of freshmen. How many freshmen graduated within 5 years? Okay? So basically, as we go down through this, we'd be looking at that amount graduated, right? So what we would do is we would take the product of those values, 0.7 and 0.6. What's 0.7 times 0.6? What's 7 times 6? 0.42, right? Okay, so 42%. So public and graduated, 42%. Okay. Other and graduated would be, yeah, it'd be down right there. So 24%. Okay. So then how many total graduate, how many freshmen total graduated? 66%. And we add those 2 things together. Okay. But think about this. So we wanted, basically, the goal was that they went to public and graduate, because when it says how many freshmen graduated, well, that means we had to have public students graduate and we had to have other students graduate, right? So if we look at this green branch, it means they had to have both public and graduate. Public and graduate meant, okay, that we need to go public times the probability that they graduated given they came from the public schools. Okay? So this would have been 0.7 and this would have been the 0.6. Because 0.6 here is that they graduated given that they were already here in these schools, right? Same thing here. Other and graduated. So we have a kind of a complex or maybe a compound situation here where I've got to find public and graduated, other and graduated, and then sum those together to get the total amount of freshmen that graduated within 5 years. Is it okay with everybody? I like to check myself with, what if they went public and didn't graduate? What's public and didn't graduate? Be 0.28, wouldn't it? 7 times 4. What about other and did not graduate? Be 0.6. 0.06. when I add those together, okay, that and that's 34%, that's 66%, is that 100%? Okay, and this is what we call a binomial situation where you have two things you can do. You can graduate or not graduate, right? You've never heard of somebody that did some third thing, correct? Okay. All right. We'll maybe come back to some of these and do another example, but I want to real quick give you a visual of some of the questions that have been asked on end-of-course exams with probability. This is one of them, okay? And this is what people somewhat dislike about the end-of-course exam, because not every single question is a calculation question, okay? Some of them are logic questions, understanding situations, okay? It says, Francisco asks the students in his school what pets they have. He studies the event shown. It says event S is that a student has a cat. Event T is that the student has a dog, okay? Now, what stinks about the end-of-course exam as well is that a lot of people think maybe event S should be labeled C and event T should be labeled D to match up with the animals, right? They do this intentionally to see if you can pay attention to detail, to see if you can piece things together and stay on track and have that attention to detail to be successful in problem solving, okay? So Francisco wants to know whether the events are independent. So Francisco finds that the two events are independent. Select all the equations that must be true for independent events then, okay? So they give us all these options, okay? And now there are squares here, and this is matches up to how we've done with Math Excel. If there's squares, you can put a check box in as many of them as you want. If they're circles, it's multiple choice. You can only pick one of them, okay? So if these are independent events, think about this, okay? What this one here says is the probability that they have a cat given that they have a dog is equal to the probability that they have a cat or a cout. I don't know what I'm doing there. Cat. All right. So is that a scenario, the way I write it that way, is that an independent situation? Yeah. Probability that I have a cat given that I have a dog is equal to the probability of a cat, which means that information about having a dog did not have any bearing on the situation. Does that make sense to everybody? So I would check this one. That's true. Okay. Now I'm going to check the next one. Does the probability of having a cat given that I have a dog equal to the probability of having a dog? Okay, so the idea is knowing that I have a dog, does that help me know that I have a cat? That's an equal sign. It was blurry when I copied it over. So the idea here is that the cat, given that they have a dog, is equal to the probability of a dog. That is not one of our conditions for making independent events true from our probabilities. I understand that we have independent probabilities from our events here. Remember, the rules were probability of A given B is equal to probability of A. Probability of B given A, so we reverse it, is the probability of B. Okay, it's always equal to the probability of that first event, meaning that this one here, I guess this is actually, if we go in order, it comes first here, but because it says given that, in actuality, this was the second thing to occur, correct? Okay. If we want to know that second event's probability based on something else that has already happened, if that second event's probability is the same as that second event's probability all by itself without knowing that something already has happened, then they are independent. So here we're saying that we know that A, the probability of A, knowing B has already happened, is the same as just the probability of A with not knowing anything about B. Does that make sense? And this is saying the probability of B, knowing that A has already happened, is the same as the probability of B without having to know anything about A. And because I didn't have to know anything about that other event over here, means that these would be independent events. This is not that situation, okay? It's cat given a dog equals probability of a dog. This has to be that situation. So we would not mark that one. Is this one match up? Probability of a dog given that they have a cat is equal to probability of a cat. That's the same structure as the one we just crossed out. Okay? So that one's not true. Is this one? Yeah, that one there is the same structure as that one. Probability of a cat given that I have, oh, I got that. Cat is S, right? So this is probability of a dog given that I have a cat is equal to probability of having a dog. That means if they're independent, that had no bearing on this probability. Okay? So we would mark that one. And then the remaining one is this one. If they're independent events and you want to know what if they happen at the same time, you take the probability of the first one times the probability of the second one. So those would be the three things you have to check off to gain the 1 point or maybe 2 points on this question. I think it's 1 point. That kind of makes sense? That's what I don't like some of the questions on the test because I think that's a very thoughtful process and trying to analyze what they're getting at here and all the ways that you can check to see if two events are independent. Yes? Say that again. Yeah. Yes. No, this one's and. This one's and. Yep. Yep. This one here, this or, that's when you're going to be talking about events that are either joint or disjoint, or we use the words mutually exclusive or not mutually exclusive, things that can happen at the same time. That's really the only time that you'll use those, and that's an addition rule. So or and multiplication never go together. So that would be maybe a visual that allows me to cancel that one out right away. Then they ask, here's a couple other probability questions that get presented. Now this is a kind of a hybrid mix of a calculation problem and a logical or theory or formula type problem where we have to understand how probability works. Okay, it says two events A and B are independent. Two events A and B are independent. That means if they're independent, remember we talked about probabilities that are independent. If A and B are independent, then the probability of them both happening is that, right? Okay, and that's the same thing as if they are dependent as well, except for if they're dependent, that probability of B has a different sample space than that probability of A did, or the probability of A that event A impacts event B. Okay, but you still multiply in independent scenarios as well. But if that's true, okay, do they give me this left-hand side? Do they give me that right there? They tell me that that's 0.24. They tell me point A, or probability of A, is 0.3. And they want to know what is the probability of B. So I can take 0.24 divided by 0.3, and that gives me the probability of event B. What's 24 divided by 3? 8. So 0.8 would be the probability of B that they're looking for there. Does that kind of make sense? Okay. All right. These are now. So in this test, you'll see a variety of. Here's a. Do you understand probability on certain depths? Okay, the test is structured, and in all tests that you take are this way. It's called depth of knowledge. There are questions that are tier 1. So basically they're saying everybody that has been awake and breathing during class should be able to get these depth of knowledge questions that are targeted to 1 pretty easily. There's a depth knowledge of 2, and there's a depth of knowledge of 3. Okay, and as we go through these questions, my hope are that you can see that this question, I think this one would be a depth of knowledge of 3, because it asks you quite a bit about trying to identify independent events. These are probably 2. Okay, this one might be borderline 1 or 2. This one's 2. Okay, so a total of 200 people attend a party as shown in the table. So the person is selected at random to win a prize. So the probability of selecting a female is 60%. Okay, now think about this, see if that makes sense. If I look at the probability of selecting a female out of how many people are there, okay, that's 12 out of 200, right? Or sorry, 12 out of 20 if I cancel the zeros. And then doesn't 12 out of 20 change to 60%? That makes sense? Okay. So the probability of selecting a child, given that the child is female, is 25%. So it says given that the child is female. Okay, so the probability of selecting a child given that that person is a female. So let's look at this. So we know it's given that they're a female. So you go into this room with 200 people. Okay, you close your eyes. You point at somebody. You're going to choose that person. Okay, so the probability of selecting a child given the person is female. So you pointed at a person, and the person next to you said, you just pointed at a female. So now you've dwindled your sample space of 200 people down to 120. Does that make sense? Okay. It says the probability of selecting a child given the person is a female is 25%. Okay. So if I know that I've selected a female, this is saying that 25% of the females in this room are children. Does that make sense to everybody? So how can I, if I have 120 and 25% are female, or sorry, 25% are children, how do I take that number and get the number of children? Multiply by 0.25. So if I multiply that by 0.25, what do I get? What's a quarter of 120? 30. Okay. You guys remember the other day, I'm just trying to draw a comparison. Remember the other day I gave you, we started class off with this table here, and it was already all filled in. This is the same style question, but you got to do a little bit of work to fill it in. And really, the only thing you had to do is find that 30. Okay? Because now working, and this is what it's referred to as degrees of freedom. Okay? Because now that I found that 30, that, and that cannot be any other numbers other than what? What should this one be? That one has to be 20, right? Okay, and once I find that one, if that one's got to be 20, what's this one got to be? 60. You got to add to 80, right? And what's this one got to be? 90, which that adds to 150. 90 plus 30 equals 120. 20 and 30 adds to 50. Okay. All right. It says the probability of selecting a male given that the person is a child is 0.4. So what I'm going to do with that, the reason they give you this is just to check to see if your chart is right. The probability of selecting a male given the person is a child. So you're going to look at this column right there. Okay. You're working out of 50 people, right? Probability of selecting a male given the person is a child. You know you're working in this sample space 50. There's 20 males in that 50. What's that work out to be as a decimal? 0.4? So that confirms that this was 30 and that was 20. which then tells me that must be right and that must be right. Does that make sense to everybody? So let's complete the two-way table to show the number of adults, children, males, and females who attend the party. So we've completed that. But what happens, and sometimes we'll ask this question, we'll say, okay, what is then the probability that you randomly choose a person that is a male adult or a female child? So how many male adults are there? 60. How many female children are there? 30. And I said or, so it means I can pick one or the other, right? So 30 plus 60 is 90. So it'd be 90 out of 200. Just a 45% chance that I could pick a adult male or female child. So they might ask a tiered question. If you fill in this table, then we're going to ask you something about those values that you had to fill in. Maybe a tier 1 question here. Sam is picking fruit from a basket that contains many fruit or different kinds of fruit. It says which set of events is independent? Event 1, he picks a kiwi and eats it. Event 2, he picks an apple and eats it. Are those independent or dependent? All right, so if we got events that are dependent, then event 2, its probability is going to be based off what event 1 happened, right? Okay, so is this probability here going to be impacted by what he did there? Got a basket of fruit here. Okay, calculators are fruit, 2 dice are fruits, the orange is the fruit, and my phone. Okay, close my eyes, pick this one out. Event 1, okay, which was this is a kiwi. I eat it. Does that impact what I choose on event 2? Yeah. So are those independent? No, those are dependent. Okay, so dependent. So when I eat it, okay, that's saying without replacement. And when you have without replacement, you're keeping it in your pocket or you're consuming it or you're just taking it out of the sample space. So then it impacts the sample space for event 2. So these are independent, so not option A. Okay. B, he picks an apple and eats it. Does that impact what he does in event 2? Yeah, so those are dependent. Event 1, he picks a kiwi and eats it. That's going to impact event 2, right? Option D. Event 1, he picks a kiwi and puts it back. So then in event 2, he's pulling from the same fruit then, right? Okay, so he picks an apple and puts it back. Those are now independent events. One does not impact the sample space of the other. Probability of flipping a coin. Landing heads is 0.5. Probability of rolling a fair number cube with sides numbered 1 through 6 in an odd number, 1 through 6. Let me reread this. Zoom out so I can read the whole thing at once. Find the probability the probability of flipping a fair coin and heads landing face up is 5 or 0.5. The probability of rolling a fair number cube with sides numbered 1 through 6 in an odd number landing face up is 0.5. What is the probability of flipping heads or rolling an odd number? Okay. This is a wordy question, but think about what this says here. It says the probability of flipping a coin and landing heads is 0.5. Okay? So probability of getting heads is 0.5. The probability of rolling a fair number cube with sides 1 through 6 and an odd number landing face up is 0.5. Probability with sides number 1 through 6 and an odd number faced up. All right, so odd number equals 0.5. Okay. What is the probability of flipping heads or rolling an odd number? Let's think about this. Probability of heads or an odd number is equal to probability of heads plus the probability of odd, right? Does that make sense? Or means plus. Now, remember, we have to remove odd and heads, okay, if these events can happen at the same time, okay? Can those events happen at the same time? No, okay, they're not. We would say that those are disjoint events, okay, or mutually exclusive. They cannot happen at the same time. So this number here is going to be 0. So what's probability of heads plus probability of odd? Be 1, right? Okay.